All right, we're live on air, whatever that means.
Just challenge of the day is kind of open this bag. So far, I'm failing.
Dom probably know how to open it. He likes this a lot.
Yeah. I was hoping to pick up my keys.
Okay.
So, if you're ready, I'll say some words. And then oh, it's even key resistant. I'll let Dom deal.
There's a little preparation.
See, I missed that part.
At least on this one.
I lose
I
it.
didn't try this. This one also a little preparation. Okay, are we ready to
Dom, can you email to the thread that we are moving here? I actually write on the board in the room, but just to make sure people.
the thread on researchers?
Yeah, researcher and HCI students.
Okay.
Cool, cool. So thank you everyone for coming to the dissertation talk for Kanit Wongsuphasawat. So I was lucky enough to know Ham actually before I even came to UW. So he actually took my course when I was still a professor at Stanford and he was doing his master's degree. And so we were both considering UW around the same time. And he said to me, he's like, I'll come to UW and not go to CMU, but only if you'll be my advisor. And I said, oh, he drives a hard bargain. And fortunately for me, I said yes. And we've had a wonderful time working together, where not only did he do the wonderful research you'll hear about today, he was also a pivotal member in actually building up the interactive data lab. So also designing our logo, helping build out the resources, but I think most importantly, helping set a really positive and productive culture and mentoring a lot of other students as well. So it's been wonderful to work with Ham. Selfishly, I'm glad he's staying in the Seattle area with a job at Apple, assuming this defense goes successfully. So, yeah.
Thank you. Cool. So I'm very excited. And today I'm going to talk about my dissertation work on augmenting exploratory data analysis with visualization recommendation. So I'd like to begin this talk with a quote from Hal Varian, the chief economist at Google, which says that now we really do have essentially free and ubiquitous data. So the complementary scarce factor is the ability to understand that data and extract value from it. To understand and extract value from this data, exploratory data analysis, or EDA, is one of the key activities that analysts have to perform in data science. And EDA is basically a practice of using visual and quantitative methods to understand and summarize a dataset prior to statistical modeling or hypothesis testing tasks. EDA typically have two main objectives. The first is profiling, trying to understand data shape and distribution, assess their data quality, and verify assumptions in the data. And the other is discovery, exploring and summarizing new insights or hypotheses from the exploration. So let's consider how an ideal exploration to look like. When analysts explore a new dataset that they haven't seen before, they typically have to perform two high-level analysis strategies. First, they should begin with a broad exploration, open-ended exploration, to familiarize themselves with different data fields in the dataset. After getting a broad overview, they may then focus on answering specific questions. For example, they might examine if a pair of fields are correlated. Investigating these questions might spark exploration of other potentially relevant fields, in turn leading again for more focused analysis. So in summary, good exploration should be comprehensive, but in terms of exploration breadth and analysis depth. However, in practice, analysts may fail to achieve this ideal exploration for many reasons. First, analysts often have limited time for their exploration. For example, from the interview study that we conduct to better understand the practice of exploratory data analysis in the wild, one interviewee says that it's okay to do EDA for a couple of weeks, but after that, I will need to start the other parts of the work. Another says that if I have to do it fast, I would not spend most of my time in exploratory analysis. I would do some spot checks like checking the ranges, but I would not even look at the distribution. I would just go right into modeling. So this is kind of dangerous. Second, the analyst may be blindsided by their own cognitive biases. For example, many novice analysts often have a tunnel vision and prematurely fixate on specific question or hypothesis without considering other potentially relevant factors. And we have seen this a lot in our data visualization class here at UW. And the final barrier is that the exploration process is tedious. As one of the interview participants says that sometimes you try a few combinations, but if you have many, many fields, even picking a few combinations of fields to visualize might be too time consuming. Another even say that if I have got more than a couple of dozen fields, then I can't really look at all the fields efficiently. So I would just duplicate the plotting. The exploration process is tedious partly because of existing visualization tools. They typically require manual classification, either via a programming language like Gplot in R or graphical interface like Tableau or Power BI. Don't get me wrong, these tools are really powerful for answering questions as they can create a variety of charts. However, to provide a complete specification for each chart during the exploration, analysts have to make a number of decisions. From a dataset like cars collection, analysts must select data fields or columns in the data table, like horsepower and number of cylinders. To summarize the data, she may then apply data transformation, like aggregating mean of horsepower by the number of cylinders. And finally, to produce a chart, she has to design visual encodings by selecting mark types such as bar and mapping fields to encoding channel like X and Y. All of these tedious steps are for just creating one chart in the exploration process. Combining this tedium with analysts' lack of discipline and time, manual classification can impede exploration and cause analysts to overlook important insights such as data quality issues or other potentially confounding factors. Given these barriers in exploratory data analysis, an open question is how might we better facilitate rapid and systematic data exploration? And to address this challenge, this thesis explores the design of visualization tools that augment manual classification with chart recommendation. This thesis makes the following contribution. First, to understand the current practice of exploratory data analysis, I conduct an interview study with 18 data analysts and contribute the characterization of the EDA process and challenges. And next, the primary contribution of this thesis is a stack of systems for augmenting visualization tools with chart recommendation. In this talk, I'll focus on the system contribution of the thesis. Meanwhile, I'll use data from the interview study to support our design decisions and highlight important future research directions. So, to design a tool that facilitates rapid and systematic data exploration with chart recommendation, we have to answer a number of questions. First, how should we design interfaces to surface chart recommendation? At the same time, how do you allow users to have control over the automation? Under the hood of these interfaces, how do we build the chart recommender engine that allows users to have control over the recommendations? And to do all of this, we need a representation of the charts themselves. In this talk, I will show you a system that I designed to answer each of these questions, starting from the Voyager visualization grammar, which serves as the chart representation. Based on Voyager, I then build visualization theory language and engine called CompassQL. And finally, I then use CompassQL to build a series of interfaces called Voyager, which enable new form of data exploration with chart recommendation. So let's begin from the foundation of this stack of tools, which is the chart representation. To support borrowing graphics, many popular visualization tools adopt the idea from the grammar of graphics by Lee Wilkinson. The idea is that the grammar of graphics can provide primitive building blocks for composing a broad range of visualizations, just like English grammar informs us how to compose words into sentences. Inspired from this idea, we designed the Voyager-like grammar for representing charts in our recommender system, and it also enables rapid chart specification as well. To support these goals, Voyager offers chart building blocks in a concise language, drawing inspiration from the Gplot2 and the VisQL language underlying Tableau. To provide concision, Voyager provides sensible default for low-level details and allow users to customize their plots by overriding these defaults. While VSQL is proprietary and ggplot is tightly embedded to the R language, Voyager instead offers a universal JSON format and an open source JavaScript library. By building on a web-based technology, Voyager can easily support the development of new higher-level system that you can see in this thesis, and also enable usage across different programming environments. So let's see how Voyager provides building blocks to create a chart using a histogram as an example. A histogram is essentially bar marks with X position encoding a binary field. The Y position then encodes the count of values within each bin. Voyager basically provides JSON syntax to define this kind of structure. First, we can describe the data, in this case from a URL, and then set the graphical map type to a bar. We can then define encoding or mapping between data fields and visual properties like X and Y. Here, temperature is mapped to X. We can also define data transformation like binning within the encoding and map aggregated count to Y-axis. Now we get a representation that reveals underlying structure or histogram. Later in this talk, I will show how this kind of representation also enables us to reason about and rank charts for recommendations. Note that this code for histogram is quite concise because Voyager automatically generates sensible default for low-level details, such as scale and axis for X and Y encodings. With the grammar-based building blocks, we can also add more encoding to the chart. For instance, we can encode weather type with color, and we get a stacked histogram. Here, Voyager automatically uses a categorical color palette to encode weather type, which is a nominal field, instead of using a color ramp, which is better for encoding a quantitative field. User can still customize the colors by overriding default domain and range scale domain and range properties. For example, here we try to make the sunny weather yellow and rainy blue, and so on. With this kind of concise syntax, we can create and recommend a variety of charts. In the latest version of Voyager, we also extend Voyager with an algebra for composing multi-view graphics with operators like repeat, concatenation, layering, and faceting. And we also present building blocks to specify interaction on this composed view. And with this new version of Voyager, all these building blocks are available in a single unified language. Since this thesis focuses on the applications of Voyager for chart recommendation, I will not cover details about syntax of view composition and interaction. But if you want to learn more about them, feel free to look at our public talk, our website, and our research paper. Before I move on to talk about how we use Voyager to enable chart recommendation, we also released Voyager as a standalone open source library. So let's talk first about its open source usage. As you can see from the example, we can write Voyager code to quickly create charts. To aid our user, we also provide online editor that helps validate and autocomplete syntax. In terms of usage pattern, we have seen people use Voyager in publication. For example, a recent book by Daniel Fisher and Miriam Meyer complete an online gallery of Voyager examples. Leading academic journals like Nature also mentioned that tools like Voyager make scientific data more accessible and reproducible. With a JSON syntax, Voyager can also serve as a visualization file format. We were excited that Jupyter Lab, which is the latest version of the popular Jupyter Data Science Notebook, already ships with native support for Voyager. The generalization syntax also means that you can use Voyager in other programming languages. Although our library is in JavaScript, other collaborators have developed native API in many other languages. For example, Altair is a popular Python wrapper in Voyager, and the feedback from the Altair community is encouraging. The feedback, so the Altair team themselves mentioned that Voyager and Voyager are perhaps the best candidate for lingua franca of data visualization. Another review by Dan Saber, which is widely shared in the Python community, also says that this type of one-to-one-to-one mapping between thinking, code, and visualization. That's my favorite thing about Altair. And of course, the underlying Voyager language. And Voyager is also widely used at many companies. And for this past few months, we have seen over 100,000 downloads since the new year. And we also received over 1,000 stars on GitHub. And in fact, the Altair wrapper in Python received almost 2 times of stars compared to Voyager. That's partly because the data science community has way more Python users than JavaScript users. So we are very excited about this adoption and usage in the industry. But the original design goal for Voyager is to support child recommendation in this thesis. So let's come back to that and see how we do that in the CompSQL visualization query language.
Sorry, you had said are we going to hear about the exploratory data analysis interview study? Seems like that's kind of important for the problem specification. We're diving into the systems, but we don't really know what the exploratory data analysis problem is.
Oh, so yeah, I'm not focusing on that because what we find from the interview also highlight other problems that can be like that can be important future directions. But for the problem that we try to tackle here is the barrier for having comprehensive analysis. So I use some of the interview data to support that, but that's not the only problem that the interview discovered.
All right, so that was a contribution to the thesis, but we're not going to hear about it in this talk.
Yeah, not the focus of this talk.
All right.
Okay, so let's see how we use Voyager to do child recommendation in the CompSQL query language and engine. So I mentioned earlier that manual child creation can be tedious. And this is in part due to the fact that users have to provide a complete specification of mark type, data transformation, and visual encodings. To reduce the tedium, one idea is to instead let users provide only part of the specification. This is actually the key idea in CompSQL. Basically, we use partial Voyager specification as a way to describe a recommendation query. This way, we can reduce the need for a complete specification while still giving users fine-grained control over the recommendation. To show how CompSQL works, let's see a basic query that replicates automatic mark selection feature from Tableau. Here we begin with a complete Voyager specification. We describe a single chart. Note that here I show the code in a table format to save space. Now we want a partial specification that asks the engine to determine the mark type. We can use a wildcard to omit mark. And given a wildcard, the CompSQL engine then enumerates candidate charts by replacing the wildcard with all possible marks. Thus, we get multiple charts that use different marks to encode the same data. However, just simply enumerating the mark types may produce charts that follow basic design principles. For example, using line or area to encode a nominal field like origin can be misleading because it can suggest a trend that doesn't really exist between these different categories. Thus, the CompSQL engine also includes built-in design constraints to prove misleading encodings. And after tuning, we still have multiple qualifying charts. The second part of the query is the recommendation method, which is for organizing results by grouping and ranking the qualifying charts. To choose one best chart, we can tell the engine to choose the best chart based on a perceptual effectiveness ranking, which we derive from prior work on graphical perception. In this case, the only wildcard is the mark. And so the ranking will mainly consider the effectiveness of mark type based on type of fields based on X and Y channel. And since bar is a better choice for encoding quantitative and categorical field, CompSQL, we choose the bar chart as the top recommendation for this query. With this query, we can replicate Tableau's automatic mark feature, which is kind of cool. However, while the automatic mark feature is useful, one limitation is that users still have to select data fields to visualize. And moreover, the goal of CompSQL is to enable new queries, not just replicating existing features. So let's see a more advanced query that enumerates both data and visual encodings. Suppose we want to see a set of pairwise relationships between all quantitative fields of a given data set. We can make a query with 2 encoding mappings and make every property a wildcard, like from mark, encoding channels, and data field. These are all wildcards. But because we want all quantitative fields, we can constrain the field to be just quantitative fields. Seeing these many wildcards, you might say, whoa, wouldn't this create so many charts? And the answer is yes, of course. We can provide a recommendation method to group redundant charts. And in this case, we want to see plots that show different pair of fields. So we group the charts by data fields that they show. So that's still a lot of charts, right? Another step is to choose the most perceptually effective chart of each group. And now we get a scatter plot for each pair of quantitative fields. To choose a scatter plot, the ranking considers both the effectiveness of the mark type and the encoding mappings. For the mark, pi is the best for encoding a pair of quantitative fields. For visual encodings, we use prior knowledge from graphical perception that people can decode quantitative values from position encoding better than length. And length is in turn better than angle and area and so on. With this knowledge, we can rank the effectiveness of encodings. In this case, we only have 2 quantitative fields, so we will use X and Y position as they are the most perceptually effective encodings. In this query, we can see a gallery of scatter plots showing all pairs of quantitative fields. As you'll see in the next section, this is actually a query that user can specify with a graphical interface. With the compare SQL queries, I then use an iterative design process to develop a series of interfaces called Voyager. In this talk, I will briefly show the original version of Voyager and its user study that motivated us to develop a second iteration called Voyager 2. I will then show the Voyager 2 system in detail, including how we use compass URL to enable new interaction methods in the system. As I mentioned earlier, that one motivation for building this stack of tool is that tedious classification can impede data exploration. With regular and compass URL as foundation for chart recommendation, we now instead consider recommendation browsing as an alternative interaction method to manual classification. This idea is actually in line with the response in our interview. One participant in our interview says that, I wish there were a tool that I can just browse through a gallery of each variable's chart. It would be awesome to just browse through each variable's distribution and outliers and then move on to the next one. So to develop a chart recommendation browser, we draw some inspiration from exploratory search systems. For example, I like to watch a movie on Netflix on weekends, but I often don't know which movie to watch. Netflix interfaces provide a few mechanisms to help me find a movie. First, I can browse around to see the collection of available and recommended movies. Second, if I have some specific intent, like unspecific intent, like I want to see a movie from some categories like comedy, I can steer the recommendation by using a facet with navigation to filter movies by category. Finally, I can also pick a movie that I like before to get related suggestions, like and pick Minions here. Inspired from this kind of browser interfaces, we developed the Voyager visualization browser with the goal to help users systematically explore more data. Voyager provides more user control by letting users select data fields to steer the recommendation. Giving a user selection, Voyager then suggests plot showing transformation of the data from raw data to aggregated data. It also shows plots suggesting one extra field to help users discover other relevant factors. As we want to consider recommendation browsing as an alternative to manual classification, we compare Voyager with a manual classification tool in a user study in which users do data exploration. For the baseline condition, we develop Polestar, an interface model on Tableau. With Polestar, users can create charts by dragging fields onto the encoding shelf. to specify visual encoding, similar to tools like that Tableau. In fact, we named the system Polestar as the research project that led to the birth of Tableau was called Polaris, and Polaris is a Polestar. With our own baseline system, we can ensure that the only differences between conditions is the interaction model. For example, all plots suggested in Voyager can be built in Polestar. For the study result, I first analyzed interaction logs to see if Voyager meets our goal to help users systematically explore more data. And we found that users interact with 1.4 more unique field sets in Voyager, confirming that Voyager helps users to explore more data. As exploratory analysis involves both open exploration and question answering, we also ask users to rate their two preferences for both tasks. For exploration, users prefer Voyager as browsing is less tedious and helps them to discover insights that they might otherwise overlook. However, they prefer Polestar for question answering as they have more control to create specific charts. Qualitative feedback from the study also reflects the complementary nature of Voyager and Polestar. One user says that I would start with Voyager, but want to go and switch to Polestar and dive into my question. Once that question was answered, I would like to switch back to Voyager. Overall, the result shows that these two interaction methods have complementary values that support exploration and question answering. As exploratory analysis involves both tasks, this result also calls for a unified tool that provides better balance between automatic recommendation and manual suggestion. To do so, I designed Voyager 2, which is a system that blends chart suggestion with recommendation in a single tool. And Voyager 2 offers multiple interaction methods in a single system. And this interaction method have varying degree of automation. We build Voyager 2 on top of Polestar, so user can create arbitrary charts by dragging and drop, like in Polestar and Tableau. Moreover, we add two new partial suggestion interfaces. Based on the main specified view, Voyager 2 shows related views to help users discover relevant data fields and alternative ways to summarize or encode the data. Finally, to give user control over the automation, Voyager 2 lets users directly auto work hard to create multiple charts in parallel. So let's see how interaction works in the demo. And in this demo, I will use Voyager 2 to explore a dataset about cars. I will highlight how Voyager 2 produces underlying computational query as well. Upon loading the dataset, Voyager 2 lists all data fields on the left. The middle pane shows the encoding shelf that users can drop fields to specify visual encodings. The main view on the right shows the specified view on the top. As users haven't specified any visual encoding, this view is initially empty. Below the specified view is the related view section. Voyager 2 initially shows univariate summaries to help analysts begin by profiling the data and without the need to create any views manually. Looking at the top left plot, you can see that most cars have an even number of cylinders. And looking at the line chart, all cars are from the 70s. After exploring each field in the dataset, the analyst may want to explore bivariate relationships between different pair of fields. Analysts can manually drag and drop different pair of fields to encoding shelf. However, repeatedly doing this can be tedious and require the analyst to have discipline to examine all interesting pair of fields. So instead, Voyager 2 provide wildcards for creating multiple charts in parallel. Below the list of fields on the left are the wildcard fields, which can be used to encode multiple data fields. And to let the system pick appropriate encoding mappings, users can drop any data fields and wildcard fields onto the wildcard shelf. For example, dropping two quantitative field wildcards to the wildcard shelf produce a gallery of scatter plots between all pairs of quantitative fields. Under the hood, the wildcards in the UI directly map to wildcards in the computational query that I have shown earlier. With this gallery, users can easily explore relationships between all pairs of quantitative fields. For example, you can see that horsepower and miles per gallon appears to have a quadratic relationship. Basically, cars with higher horsepower tend to have less miles per gallon. To see what's the outlier point, we can interact with the plot and hover over the point to see a tooltip. And using the bookmark button, we can also take some notes about our insights as well. To further drive recommendation based on this view, we can use the focus button to promote this view to be the main view. Clicking the button updates both the encoding shelf and the specify view on the top. Based on this specify view, Voyager 2 recommends different kinds of related views. The related summary section suggests alternative ways to summarize the data. For example, from the scatter plot above, we can see a 2D histogram of the two same fields. Under the hood, Voyager 2 generates related views by inferring a query from the main view. So, from the main view, suggestion of the main view, Voyager 2 adds wildcard to the transformation function and the marks to generate related summaries and suggest different ways to summarize the data. Voyager 2 also use similar query inferencing techniques to generate other kinds of related views. For example, scrolling down more, we can see the field suggestion sections, which add one additional field to specify view. The goal of this field suggestion section is to help analysts discover relationships that they might otherwise overlook. From the demo, we have seen how a user can use and transition between these interaction methods to perform data exploration. So now that we have seen the interface, next I'm going to show the evaluation of Voyager 2. Again, we conduct a user study comparing Voyager 2 with Polestar, and this study design allows us to directly contrast the effect of the new partial fixation interfaces over pure manual fixation. So let's see the result. Similar to the prior study, we analyzed if Voyager 2 promotes data coverage. We found that users interact with 2.4x more unique fields in Voyager 2, similar to the prior version of Voyager. We also analyzed user rating for each task. For open exploration,
it's normally the connection in the thing, like normal.
okay.
We just entered greenfield research.
Yeah.
Okay.
So Instagram filter, hands and stuff.
It doesn't look that bad on stream, though.
Everyone can stream.
I think the pretty picture's over anyway, right?
Yeah.
Ooh, there we go.
I guess.
Yeah.
Okay. Okay. So for open-ended exploration, user favor Voyager 2 over Polestar, similar to the prior study. However, for question answering, user rated Voyager 2 as comparable to Polestar. And keep in mind that Polestar is based on the interaction method that's based on years of usage in industry. So this is actually quite a feat for being comparable to it for question answering. And since user prefer Polestar over Voyager in the prior study, we can say that Voyager 2 improved over the original Voyager for question answering, and overall we can conclude that Voyager 2 improved over both Polestar and Voyager for supporting both tasks. Despite having more features than Polestar, Arjun also expressed that Voyager 2 is easier to use. One said that, I like that Voyager 2 showed me what fields to include in order to make a specific graph. With Polestar, I had to do a lot of trial and error and couldn't express what I wanted to see. Another mentioned that I feel more confident using Voyager 2. It helped me to learn. To summarize, Voyager 2 presents a set of interfaces that blend chart fixation and recommendation browsing in a single tool. Overall, the study shows that Voyager 2 can facilitate both exploration and question answering better than existing tools. Taking a step back to see the bigger picture, I have contributed foundation for chart recommendation, including the Voyager-like grammar for representing charts, and the compatible query language and recommender engine. Based on these foundations, I have built the Voyager and Voyager 2 interfaces to enable new form of visual data exploration with chart recommendation. Besides supporting data exploration, this system has also served as foundation for new applications and research projects. Earlier, we have seen Voyager being used in data science via Jupyter Lab and a wrapper like Altera. And in a collaboration with Jupyter team, we are also integrating Voyager 2 as an extension in Jupyter Lab, so we can help user easily transition between data exploration and other analysis activity in a single environment. Besides industry application, each of these tools has also enabled new research projects. For example, we have built a model for automated reasoning about visualization similarity and sequencing on top of Vega Light. Our colleagues at Georgia Tech and Stanford are also working on different natural language interface for data visualization based on Vega Light. Compass-L is also used to generate training data for a system that reverse engineers visual encoding from bitmap chart images. And earlier this year, Dominic has built on Vega Light on Compass-L and developed a chart recommender engine based on answer set programming, which makes it easier to extend the constraint and learn ranking preference. Voyager 2 has also been extended for studying other issues in data analysis. For example, my colleagues at UW and Microsoft Research have extended Voyager 2 to study free-form annotation in data exploration. Going forward, I see many research directions that this thesis can be built on, both in terms of exploratory data analysis and visualization recommendation. For exploratory data analysis, this thesis successfully applies chart recommendation to facilitate open-ended exploration and increase data coverage, as we have shown in this study. However, this kind of automation doesn't come without danger at all. One potential danger is whether automation will lead analysts to be complacent and think less, or bias them toward spurious discovery. For example, one participant in the Voyager 2 study mentioned that these related views are so good, but it's also spoiling that I start thinking less. I'm not sure if that's really a good thing. Thus, important research going forward is to study the effects of automation in data analysis, so we can ensure that future data analysis tools have the right balance between automation and user control. We can actually use the tool that we built on this thesis to further study this issue. For example, I know that Francis is planning to study whether automatic inclusion of uncertainty information will affect the rates of fault discovery in data exploration. Moreover, from the interval study that we did, we also find other issues in exploratory data analysis that should be issued. We found that one big challenge in data exploration is not just getting the data set and try to plot things. Another big issue is trying to find and pick data sets and data fields that are relevant to their analysis. And this often rely a lot on domain knowledge. However, oftentimes analysts do not have domain knowledge that they need and have to rely on other people like database owner or their clients or analysts that are consultants. For example, one of our participants says that I have to go around ask people like, okay, so you work on this team. Is there any place I can find this data? So this is just one example of many cases that people have to depend on other people. And this kind of dependency actually a major cause of delay in data exploration. For instance, one interviewee said that a lot of time we need domain expertise from our clients, but it takes time to wait for them to respond to us. A round of communication may take 2 days. And from the interview study, we find that a lot of time data exploration may only take a day or two for the actual exploration, but in practice, it takes like a few weeks because of this kind of delay that they have to rely on other experts. So future data exploration tool could better help analysts discover relevant data, especially when the same data sets are used for multiple different analyses. One critical question is how do the tools can collect this kind of relevancy information so that they can surface this information and make recommendations to users. A few options include like trying to learn from user interaction. As user interact with certain field together with another fields, maybe we can infer some relevancy from that. And in addition to that, if we can provide a lightweight mechanism so that user can annotate this dataset with a bit more information so that the tool can use this information recommendation, that would be so useful too. Besides finding relevant data, another relevant issue is finding relevant analysis. One participant says that, well, we don't have really a very good way of sharing what everybody else has done. And in addition to not knowing what others have done, analysts also have problems with what they have done too. As another participant said, well, it often happens to me and to most analysts that you go through an awful lot of charts and they're like, oh, there are 3 that I actually want, but I didn't save them along the way. Based on this problem, another important research question is how might we help analysts better access their own and their colleagues' exploration history so they can know what they have done or what others have done and don't do repeated work. Beyond exploratory data analysis, another exciting area of work is to use this foundation for child recommendation to enable new applications. And some of these applications will actually further drive visualization recommendation research. For example, to develop natural language interfaces for data visualization, one promising approach is to map natural language commands to visualization queries like SQL, and let our visualization recommender determine the output. As natural language command may include the tasks they want to perform with the chart, such as like seeing if 2 plots are correlated or seeing if a variable predicts another column. So a critical research is to extend the chart recommender with task-based suggestions. And besides authoring and exploring charts, another common task for data visualization tools is dashboard creation. You can imagine a system where you can specify information that you want to show up on your dashboard, and the system automatically produces an interactive dashboard for you. To support this system, you need to work on a number of challenges. First, what should be the query language and interface for specify user intent for getting the dashboard that they want? Moreover, visualization research has been focusing mainly on the effectiveness of a single chart. To suggest a dashboard, we have to study and design new constraints for multi-view display. For example, Jennings has done early work on consistency between visual encoding between subplots in a dashboard. And finally, as we go from single static chart to interactive dashboard, the space of possible design will grow exponentially. Thus, we have to scale our recommendation model to this large design space. The Drago project by Dominic already laid some groundwork for an extensible recommendation model. However, we still need an efficient strategy to collect training data that covers this large design space. Besides graphical interfaces, plotting APIs like ggplot and Altair are still a common way for chart authoring. We could apply chart recommendation infrastructure in this thesis to improve user experience of these APIs too. For example, we can provide linter to help users avoid misleading designs when they try Altair commands, and also suggest better design alternatives. And finally, for all these different applications, one important lesson that we learned from Voyager is that recommendation can help users learn. Like one user said, I feel more confident using Voyager 2. It helped me to learn. To help users learn even more, we could extend chart recommender to provide explanation why certain designs are better, why certain designs are bad. This way, our tool can also help educate novices and improve visualization literacy. So lastly, before I end this talk, I would like to use this opportunity to acknowledge so many people that support me through this PhD journey. First of all, I would like to thank my family, especially for my parents, for their unconditional support and love since I was born. My PhD journey here also led me to meet my fiancée, Dear, who has since provided me support and energy and love in every day. I also would like to thank my brother, Chris. Without him, I might not be even standing here defending my thesis today. Long story short, I was doing my master at Stanford, like Jeff mentioned, and then my brother Chris was then doing his PhD at Maryland with Ben Schneiderman, which of course you know is also in HCI and visualization. At the time, I felt it must be quite a stupid idea to do a PhD in the same area as my elder brother, but Chris insists that, well, at least I should take the data visualization course at Stanford, before the professor there was the best guy in data visualization. don't tell Ben. And as you probably know, the professor Chris talked about was Jeff's younger self.
Sounds about right.
I don't know. He's not that long younger.
And his data visualization class was one of the most fun classes I've ever taken. More importantly, it convinced me that we can actually impact and change people's life through research, basically changing the way people work with data in our case. And knowing that Jeff was moving to UW, so I applied to UW and became first PhD student of Jeff here, as he mentioned earlier. Fast forward 5 years, I get to achieve what I hoped to do. Our work has made a lot of impact, both in research and in industry. And Voyager has also become part of Jeff's picture on Wikipedia. And I've learned
by Dom, I think.
Yeah. I've learned from Jeff to be a better researcher, engineer, designer, and a better person. And despite his duty as a professor and a co-founder of his startup, Jeff has also led by example and shown what it takes to make impact through research by implementing all these versions of Vega that my thesis has built on. Like even this morning, like I still see some commits on GitHub that he's making right before this talk. I think it's hard to cover all the great things about Jeff, but I'm definitely lucky to have such a smart and caring advisor like Jeff. Thank you. And in addition to Jeff, I'm also have the luxury of support from many mentors over the years. I would like to give a special to Job, Bill, and also Anushka for mentorship and collaboration for these past 5 years, especially to Job, who generously let us build on the idea that we have from my internship at Tableau 5 years ago, and that has become the thesis that you are seeing today.
It's pretty cool.
Many people also say that PhD can be lonely as we have to work alone for 5 or even more years. That has never been the case for my experience. For all of these projects, I've been lucky to collaborate with many wonderful lab mates in Interactive Data Lab, especially for Dom, who co-authors all the system paper in my thesis and hang out on GitHub with me almost every day. And also for people who are listening on the stream, he also set up the live stream today too. I'm also grateful to work closely with Arvin, Yang, and Yang-kun, and to receive many useful feedback and encouragement from the group throughout the years. In addition to wonderful lab mates, I would like to thank all the undergrad research assistants and Google Summer Code students, as well as many wonderful collaborators in the open source community that contribute to Vega-like Compassive and Voyager. And to give you a sense of how fruitful collaboration we have, Vega already have over 6,000 commits, and earlier this morning we have our pull request / issue number 4,000. So couldn't resist to add it to this talk. And besides work, I would like to also thank all the UW and Seattle friends for all the fun we have over the years. Like some examples include like funny sport like inner basketball. We also went hiking, and we also have potluck party, and of course some World Cup library within the group. Sorry though. And with that, I'm happy to take questions.
Keep going. 3 minutes.
Yeah, so we start with public questions. So I encourage non-committee members to lead off.
I got kind of a high-level question.
Yeah.
So you were talking about the importance of coming up with data and data lake as like a visualization grammar, and you were kind of just dancing around the question of like, how do I change the semantics of what I want to know into this? So do you see Voyager and say like NL or natural language interfaces as being like the the way to translate like the semantics of what I want to know about the data into this grammar? And what do you think are the kind of like next steps?
Yeah. In terms
taking advantage of it?
of transferring semantics, one of the things that we learned from all this experience that you should think about the semantic, but they don't have a complete picture of what they want in visualization in their head. Like traditionally, if you look at tools like Gplot or Tableau or even Voyager, like manual specification is kind of like more like iterative refinement process. Like you kind of like, oh, I want this, but you actually don't know everything you want, and you specify some information to the tool, and you see some result output, and then you realize that you missed something, and you add more information to the tool to get exactly the chart that you want. What we do in this work is basically advancing the notion of partial specification, like letting users find part of their want and try to use recommendation to fill the rest. And Voyager is a step toward that, in the sense that we provide GUI that have wildcards and augmented with recommendation. Obviously, interface like NLP may bring us closer to what people have in mind. At least we actually think in terms of our language. So at least being able to express that is one direction. So going forward, so there are many applications we can try to do this, right? Like as I mentioned in the future work direction, like trying to use it with different interfaces and trying to apply to recommend other kind of chart. Like in this talk, we only mostly recommend a single partition plot. But what if you want to do recommendation for dashboard or multi-view plot? So that's the future direction.
So you talked about related work kind of at especially a broad level, which I thought was really interesting and cool. Like it's like the natural language interfaces. I'm curious for the particular design of Voyager itself. What are some parts of kind of recommendation and exploratory data analysis that you think it doesn't really develop right now, and how you could kind of make some more incremental type changes to that it would improve its usefulness for exploratory data analysis?
Yeah. So one of the things that we explore mainly in this thesis is like the architecture and the system of things that we have to build, and we also try to explore if like adding recognition to the interface is helpful at all. But in terms of optimizing what should be recommended, in Voyager we mainly suggest additional field by enumerating all the fields. Obviously, that might not scale, especially from the interview study. We see that people actually work with data that has so many variables. But then the tricky part is not. So people also have done using statistics to recommend charts. But what we find from the interview study is is that people don't focus so much on this field has correlation or so on. They actually care much more about semantic and some tricky domain knowledge, like this field actually the same as another field, but it has some minor correction, those kind of things. These are the things that challenging for people in their explorations. And currently, the tool do not have any information about this. If we have a way to embed more of this information in the tool, then exploratory analysis tool can facilitate people's job way better.
Who has used Voyager on their own data as opposed to data you provided as part of the user study?
Can you say
who has used Voyager on their own data?
So we have seen people like every now and then say, I have used this in the exploration, mostly in class. I know that, for example, Greg has his student use Voyager in his data science class. But for broader public adoption, one challenge that we have to do is like trying to scale this recommendation for larger data set. So far, the release that we have in the open source is a research prototype, so it's not like scale to large data like product like Tableau, of course.
So large data is what you see as the first bottleneck?
Yeah, that's a first bottleneck.
So a lot of visualization libraries, like for example, some wrappers around ggplot and R and other custom libraries people have written, will take their data set and do like a kind of all combinations of fields type visualizations. I'm curious if you've compared your tool, there's something that's like that. So like we compared Polestar, it was like kind of a very different style of interface. I really like the results where you were like, oh, Voyager is good for this, not so good for that. How do you think Voyager compares against something that's kind of more like what it is?
So I'm not sure I get the question. So
like a SPLOM, like if you make a scatter plot matrix, for example, is like an example of a library call that you can make one call and then get a bunch of overview plots. So I'm curious if you compare it to that.
Yeah. Yeah. So SPLOM is a very specific set of visualization, right? Like you only show scatter plot in the matrix. So with tools like Voyager, you can flexibly choose so many kind of different visual encodings. And if you look at the Voyager Lite tool, you can actually make things like SPLOM tool or make other things and also make it interactive. So that's the other thing that we do different from this existing tools.
So you mentioned that recommendation based on the data properties may not be what people want. What do you think future recommendation will do? Will it just be purely based on finding good encodings, or what do you think will be the direction for recommendation?
Yeah. So we talk so far in this talk, we actually do mostly recommend good visual encoding for given data, and we just enumerate a lot of them. The other part that I mentioned briefly is like we actually have to consider what tasks people want to do, and for some tasks like finding correlation, you might want to do scatter plot, or you want to see something predict another variable, showing regression line maybe better. That's one direction. And the other tricky part is like what are the important data, which is kind of tricky to recommend in the sense that first of all, how to know that. And second, how do you make sure that when we recommend that, we don't make people become complacent and think about other things that the system doesn't know. So we have to try that balance for recommendation too. So
I'm curious, like, how do you distinguish between data analysis or like data exploration and data analysis, and like specifically statistical analysis? So like, you give someone 20 scatter plots in Voyager. Humans are really bad at saying, oh, the R value here is good, or there's a high correlation. So like, do you think it's important to like show some statistics inside of this as well, so that you that individuals can better say, oh, this might be important, rather than just saying, oh, this looks important?
Yeah, so exploratory data analysis is a part of data analysis, and when Tukey kind of start like this idea of exploratory analysis, he trying to make it clear that there are like at least two kinds of analysis. One is like exploratory, which is when you're not trying to confirming anything, but you try to go around and see what data contain, if there are interesting hypotheses. So that's one part. When you do like doing like p-value and those kind of things, that's the second part, which is confirmatory analysis. When you like, okay, you have this specific hypothesis that you want to test it, and actually it's important to separate these two very clearly, both in terms of the process and the data that you use too. Because if you explore something and you find something and you use this hypothesis testing technique to verify the data that you use to explore, then you might run into something that is discovered by chance too, right? So.
So I think it's useful for everyone to have you talk at least a little bit about the study that you did at the beginning, who the subjects were in particular, and also you sprinkled throughout your entire talk quotes from people, but I don't know who they were. Oh, yeah. I don't have any sense of of that, and I think that that's important. It's actually very important because it shows the how broad or how exactly what your contribution is. And so at least talk to it for a couple of minutes, because I want to know who those quotes are from and who you studied on EDA in particular. Remember, Tukey was a statistician, and so he was very focused on people skilled in statistics. And was that the set of people that you were studying?
Yeah. So we recruit people who are data analysts, scientists from the industry, and also people who are researchers and use like exploratory analysis as a part of their work. So we interview 18 people, and I think about 12 of them are from industry and 6 are from research. And so there are a couple of other findings that I didn't include here. So one of the things is in EDA we talk about like what is the goal of exploration. And from this study, we actually also find that there are two kind of goals that I mentioned briefly at the beginning. Like one is kind of like just checking profiling the data, like checking if the data looks reasonable, verify assumption, but not trying to learn so much from it. It's more like checking if this is has good quality. And the other goal, which actually happen a bit less common, but still happen, which is more like discovery, like trying to find interesting insights or hypotheses. So that's one of the things that I didn't mention so much here. And then we also find that we also find that this different data analysts also have different measure of work. Some are embedded into some domain, so they have a lot of domain knowledge. So the part that I talk about domain knowledge might not be so hard for them because they know a lot, but they're also analysts who work pretty much like a consultant. And because of that, they are good at data analysis, but they do not have the domain expertise in the area that they have to do an analysis. And that they have to depend a lot on.
And then talk a little bit about the subjects that you had using the Voyager and Voyager 2 and how much they understood about the data sets that you used in those studies.
Yeah.
Because obviously, I mean, part of the reason I'm pushing is because, yes, some analysts are absolutely they have deep domain knowledge. Even the ones that don't, after a while, when working with domain experts, do acquire that expertise. I just know that it's the reality of studies that you can do anywhere, but particularly in university, that people are more shallow in terms of their domain expertise.
Yeah. So in Voyager, both Voyager study, we use like a sample data set, like from like movie and website. So the people who do analysis are people who do like use EDA in their work, but for the study, they have to use our fixed data as a control variable. So
yeah. Yeah. And what was it? And how much understanding did they have of the data set that you kept constant across all the subjects?
So for the Voyager study, because we picked a topic that's kind of like accessible to general people, like movie or like planes, so it's kind of not that hard for them to like be engaged be engaged in the exploration during the user study. But in practice, then it's not always the case, right? Then it's the objective is part of their work, even though that's not their domain. They have to.
We'll talk about this some more. But one thing is that for the exploration phase, yes, that is sort of a more superficial thing.
Yeah.
But when you actually need to really sort of start to dive in, then that's when the domain expertise becomes more critical in terms of actually helping people get their work done.
So there's an advantage to that you just expressed of using an accessible data set, right? When you can design a user set, you don't have to worry about that. Is there a disadvantage to using an accessible data set?
Oh, yeah, that's definitely a disadvantage because like if you want external validity, then having them doing analysis of say if we deploy Voyager in their real life and have them use it, that might have more external.
Well, I guess I'm fishing for something a little more. It seems to me that accessibility is sort of in tension with exploratory. Right? If something is accessible, sort of by definition, doesn't need to be explored. If you're familiar with it, you don't really.
I would disagree with that because even though you know about movie, you don't know the distribution of say how their profit are distributed or how their rating are distributed. So while they are exploring, they kind of know, oh, what movies mean, what is movie genre, what's comedy, but they don't know, oh, that's comedy movie makes more than drama movie, or those kind of things. So that's the value to explore the data and engage with it. If you look at website like 538 or their data are actually data that are pretty much accessible to us, but they dive into the data and try to extract interesting bits from those data for us. So having domain that accessible doesn't mean that it's not worth exploring.
I agree with that, but I think there's an area of exploratory data analysis that you haven't been able to really touch on because the examples are all very familiar to people. And I think in some cases people are dealing with unfamiliar data in some sense, and there's insights that might be gained there. But I think it's
necessary step of breaking apart what we mean between what is a familiar domain and what is familiar data, because those theirs are completely independent. So I'm not sure what we're talking about. But we're also at a time where I think we should probably move to the closed session. So maybe a last question from a non-committee member.
So I'm wondering if you talked a little bit in answering an earlier question about sort of the domain expertise of the people that you interviewed and the people who participated in your studies, and how that's kind of informed by where they're coming from. But I'm wondering about how the context in which people are doing exploratory data analysis, more with regard to the kinds of like organizational imperatives that are driving them to explore the data, might impact their goals in exploring the data, and perhaps even their likelihood to try to act on or make a recommendation based on a spurious finding. I'm wondering if you found anything about that in your interviews.
So I don't think we find anything specific to spurious finding, but in terms of context of why they are, one thing that we see for sure is that in people who do analysis for their job, they usually, even for exploratory data analysis, they usually have some high-level objective. So it's not totally open-ended. It's like, oh, I just have fun with data. In the sense that, like, in our user study, that might be not as valid as in the real world, in the sense that, well, you just have fun with movie data or birds, right? But in reality, they may have some goal, like if you're working for some ads company, they might want to see why certain ads do well or not, or like why are there certain a lot of spam for some region for certain day. So even though they pretty much will have some high-level objective, but still they have to do exploratory analysis because they have to explore so many different data that they have on those days that the spam occur, and try to see what actually the reason that caused those kind of things. So given that they have higher level objective, they're not doing totally free-form thing. They have some scope, but they still do exploration because sometimes, a lot of time, the questions are open-ended. So that's.
So you're saying there's some aspects of exploratory data analysis which are sort of universal, like certain checks that you have to do, certain things that you want to know about the data set that you do regardless of your goal?
Yeah, so I think let's put it this way. So that's like everyone pretty much have to do check. Even if the question is not open-ended, everyone have to do check. But if sometimes the question is open-ended, then you have to do more the discovery that I mentioned, right? So that's like the hierarchy of importance there. Pretty much you always have to check, no matter you have fixed question or not. If you have open-ended question, then you want to do a broader discovery as well.
Right. Thank you, everyone.
Thank you everyone for coming.